All right, section 5.2 introduces probability models and some basic rules on probability, some theoretical probability stuff. So first of all, a definition, a sample space, and a probability model. So a sample space, usually we use S to denote the sample space of a chance process, is just the set of all possible outcomes, or the list of all possible outcomes. And then a probability model is a description of some chance process that consists of two parts, the sample space and the probability for each outcome. So a sample space is a list of all possible outcomes, and a probability model would be the list of the outcomes and those outcomes associated probabilities. So first, list the sample space for each of the random phenomenon. One thing that I think helps keep things clear and minimizes confusion about a random phenomenon is to understand that a random phenomenon is just a thing, but you really can't talk about probabilities or sample spaces until you talk about what you record from that random phenomenon. So, and I think this example kind of illustrates that. It'll help us keep clear some of the confusion with probability. Number one, flip a coin 3 times and record the sequence of heads and tails. So I'm flipping a coin 3 times. There's the random phenomenon. But I'm recording the sequence of heads and tails. That tells me what my sample space is going to look like. So my sample space S, and you could just list them out. You don't have to use this fancy notation, but the sample space S would consist of, it's the set of all possible sequences of heads and tails. Heads, heads, heads. Tails, tails, tails. So let's list all the outcomes that have 1 heads and 2 tails. Heads, tail, 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 head, tail, 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 head. Let's list all of them that have 1 tail and 2 heads. Tail, head, 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 tail, head, 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 tail. So looks like we have 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes for this random phenomenon where this is what I record. Okay? Second example, flip a coin 3 times, record the number of heads. So exact same random phenomenon, but what I'm recording is now different. Now I'm recording the number of heads. Well, what's the smallest number of heads you could get? Well, you could get 0. You could get 1. You could get 2, or you could get 3. Notice the exact same random phenomenon has very different sample spaces depending upon what you record. And the probabilities are going to be different as well. Okay? Roll 2 dice and record the sum of the faces showing. So I'm recording the sum of 2 faces. So the smallest sum would be 1, 2, like a 1 and a 1. Now, if I was recording the number, the faces of the die, I'd record like little ordered pairs, but I'm not. I'm recording the sums. So 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and then the biggest sum I could get would be 2 6s, right? So we're going to go up to 12. That would be the sample space. Roll a die and record whether the outcome is even or not. I roll a die and I'm going to record even or not. I guess I could put not even, or I could record not, or I could record odd. Not exactly sure how I'm supposed to record it, but however I decide to record it, that would be the other outcome. All right, so let's talk about probability models. Probability model, remember, lists the sample space, all the outcomes, and then their associated probabilities. That's what makes a probability model, if you will. A probability model lists the sample space and all possible outcomes and the probability of those outcomes. One of the 2 examples below is not a probability model. One is a probability model and one is not. Identify them, explain why one is not a probability model. All right, so X is the number of car repairs, so we could have 0 repairs, 1 repair, 2 repairs, or 3 or more. Now you kind of might say, well, wait a second here, this isn't an outcome. This is a combination of outcomes. And you're right. Usually we'll call this an event. An event is a combination of several outcomes, for example. However, if I'm recording 0, 1, 2, or I'm recording 3 or more, then this is actually an outcome. So how I define my outcomes is kind of up to me, or up to the person that's recording the outcomes, right? So here's the associated probability. So the question is, are these sensible probabilities? Could these work? Well, 40. So first of all the probabilities are between 0 and 1. If I add them up, 40 plus this is 75, plus 10 is 85, plus 15 is 100. So these are all the outcomes. My probabilities of those outcomes add up to 100%. So all possibilities are accounted for. I don't have any extra. There's no bad probabilities. So this is a good model. Grade on a test, A, B, C, D. So the question you have to ask is, are those all the outcomes? Well, if everyone got either an A, B, C, or a D, then that is all the possible outcomes. If somebody got an F, then we're missing something. If somebody got an A minus or a B plus or all these other ones, maybe we're missing things. But again, the question is, how were the grades recorded? What outcomes were there? And I don't really know. The probabilities are 20, 40, 30, and 8. So this adds up to 60. This adds up to 90. This adds up to 98%. So when I look at these, this may be the sample space. I don't know. However, whenever I add up the probabilities, I'm only account for 98%. So that means 2% is left over. That means there was another grade. Maybe it was an F. I don't really know what it was. But there must be another grade that is missing. And if there's a grade missing and there's probabilities not accounted for, then this is not the sample space, and this is not a probability model because it doesn't describe everything. Create a probability model of the following. So the random phenomenon is we're going to roll 2 die and record the sum of the faces showing. So I think I listed the sample space here. Okay. So let's say X, and then we'll say the probability of X. So I got 1, 2, 3. Ooh, I might need a little bit more space. Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. There, that was exciting. Now, you might make an assumption and say, well, if there's not 12 outcomes here. There's actually, dang it, there was no 1 for an outcome. The first outcome was 2, right? Because you can only get a sum of 2. Lowest sum you can get is 2. The largest you can get is 12. So you might count these up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 11 outcomes. Well, if you assume all these outcomes are equally likely, then each of their probabilities would be 1/11th. And if we add them up, it would add up to 100% or 11/11ths, and everything would be all fine. The problem is I'm not so sure in this random phenomenon that these events are equally likely. For example, there's only one way to get a 2. You'd have to have a die of 1 and another die of 1. However, a 7 can be gotten a lot of different ways. You could get a 3 and a 4. You could get a 2 and a 5, right? And you could also get a 5 and a 2. So I think these are not equally likely. And so we can't assume that they're equally likely, or we're going to make some mistakes. So how can we organize this? One way to do it is to kind of create a list of outcomes if I was recording the faces. So if we had die 1 was 1, 2, 3, 4, 5, 6, and die 2 had a 1, 2, 3, 4, 5, 6. And if I create this little grid, this will have all the outcomes. Basically, I'm listing every single possible set of face values when I roll 2 die. And the reason this is going to be helpful is I think you're going to see that these squares are actually equally likely. Why? Well, when I roll a 6-sided die, assuming the die is fair, ooh, they should have said we'll roll 2 fair die. The die is weighted, or there's problems, or it's not machined properly, or there's rounded edges or anything, these outcomes may not be equally likely. But if we assume that they're two fair die, then these 6 values are equally likely. And these 6 values will be equally likely. So if all of these are equally likely and all these are equally likely, then every combination of these squares should also give us equally likely outcomes. So now let's add up the faces. If I get a 1 and a 1, I get a 2. 1 plus 2 is 3, 4, 5, 6, 7. 2 plus 1 is 3. 2 plus 2 is 4, 5, 6, 7, 8. And I think you're going to see as you go across here, you just kind of keep adding 1 across and adding 1 down. Add across, add down. And notice we got all of our outcomes. So how many outcomes are there total? How many equally likely outcomes? Looks like there's 6 times 6, or 36 individual squares. And since these individual squares are equally likely, as I justified, we can just calculate how many, we can just add up how many outcomes there were. There's 1, 2. So that's 1 out of 36. There's 2 3s. So that's 2 out of 36, also known as 1 out of 18. Actually, you know what? I'm not going to simplify these. You might say, well, man, you need to simplify, but well, whatever, I don't care. 2 out of 36. There's 3 out of 36 4s. 4 out of 36 5s. 1, 2, 3, 4, 5, 5 out of 36. 7, there are 6 of them. 8, now we go, so we're going up the chain, and then 8 is 4, 2, 3, back down the chain. 5 out of 36, 4 out of 36, 3 out of 36, 2 out of 36, and 1 out of 36. And if you add these up, you'll get 36 out of 36. So this is a probability model, and notice the outcomes are not equally likely. Okay? All right, very good. So in class, we were going to talk about events and some of the basic probability rules, okay? But the homework quiz that you're going to see tomorrow will be on sample spaces and probability models and maybe some of this stuff here.